All right, well, welcome back, everyone. In today's video, we're going to cover Thevenin's and Norton's theorems, and we're also going to revisit problem-solving strategies for more complex circuits. You may recall in previous videos, we talked about some strategies about how to use node and mesh analysis and when you'd want to use each one, and you'll see with Thevenin and Norton's theorems, it helps to have some strategies to know how to approach these problems. So we'll also take a closer look at ways we can better determine which tool in our toolbox we want to use for a given problem. All right, goals for today. By the end of today's video, we'd first like to cover strategies to help you more easily determine which approach to use for a given circuit problem. Up until this point in the class, it's often been fairly clear which strategy we want to use. What you'll see with the Thevenin's and Norton's theorem is sometimes it's a little bit tricky to figure out where to start. So we'll talk about strategies that you can use to help make those problems more straightforward. Next, we'll learn about Thevenin's and Norton's theorems. And we'll see that these theorems are very powerful, and they can help us simplify and solve significantly more complex circuits. And finally, we'll continue practicing additional examples of all of these tools to gain more intuition and experience. And so as much as possible, I highly recommend that you try the examples that we're doing today on your own and verify that you're able to get the same result as we do here. By practicing these problems, you can get more comfortable with the strategies, and you'll find once you know how to approach these problems, they're actually pretty straightforward. So let's first begin with strategies. So I'd like to share some very helpful strategies to identify which approach to use for a circuit problem. We've covered a lot of different tools so far, such as node analysis, Kirchhoff's laws, mesh analysis, source transformation, superposition. So it helps to keep all these tools in a running equation sheet. If you haven't already done so, I highly recommend making that equation sheet and have it handy as you do practice problems. Next, make sure you read questions carefully. This might sound kind of silly, but sometimes we're in a hurry, we're reading questions fast, and we miss important information. So be sure to recognize your knowns and your unknowns in your circuit's problems. Another extremely powerful strategy is to draw a picture and ensure your relevant information is labeled. Many students often get stuck on problems because they're having trouble visualizing the circuit and really seeing what all the knowns and unknowns are. But if you clearly label your knowns and unknowns in a circuit picture, it can be a lot easier to figure out what more information do you need and what information do you have. Also, drawing a picture can help you get more partial credit on homework and on exams. Next point, simplify further if you can. So you may come across problems where there might be some resistors in series or parallel. Maybe you have an open or a short circuit. Maybe your circuit could be rearranged a little bit in order to make it in a more convenient state. So watch for that low-hanging fruit, right? Call this low-hanging fruit. Because these are kind of easy bits of information, easy unknowns that we can solve for to make our life easier. So if you do see something in your problem that you can quickly and easily determine, might be a good idea to go ahead and simplify further. Number 5 is also a very helpful strategy. Is there anything special about the circuit? So in this case, you want to watch for special cases of our different tools. For example, if we have a voltage source between two nodes, we may be able to use a supernode. Or if we have a current source that is shared between two meshes, maybe a supermesh would help us simplify. Dependent sources, switches, opens, shorts, these can also provide us useful information and hints about where we might want to start with that problem. And so definitely watch for those special cases and see if they can help you simplify your questions. Number 6 is a strategy we've mentioned in prior videos, but I think it is a very important one that is worth mentioning again. Count the nodes and meshes. And remember that node analysis and mesh analysis can both work, but sometimes one is easier than the other. If a circuit has fewer nodes, you should consider using node analysis to solve that question. You might be able to solve your entire problem with just one equation, instead of having to write several mesh equations. Similarly, if your circuit has fewer meshes or fewer closed loops for current to flow, consider mesh analysis. Maybe instead of having to write equations for several nodes, you could just write one Kirchhoff's voltage law equation for your mesh. So keep that in mind. And also watch out for those supernodes and supermeshes. Those can also help simplify questions considerably. Finally, check the sources. If you have a circuit that contains multiple independent sources, superposition might be able to help. Remember, superposition allows us to consider each source's contribution separately, and we only need to solve for one source at a time. Also consider source transformation. Maybe if you changed a voltage source into a current source, or vice versa, that might enable you to solve things more easily as well. And finally, this last point, can you consider a smaller part of the circuit? Maybe your circuit as a whole is big and ugly, but maybe you could apply Kirchhoff's laws to a smaller node or just a closed loop within that larger circuit, and that might allow you to determine some useful information that you can use to solve the rest of the circuit. So as we go through the examples in today's video and in future lectures, I highly recommend you keep these strategies in mind. And as you see a new circuit problem the first time, try applying these strategies and see if they help you solve those questions more easily. Often there is more than one possible approach that can be used, but often one approach may be easier than some of the others. Let's do a quick example before we move on. Here's a quick example. Suppose I wanted to solve for my voltage Vx. Vx is the voltage across this unmarked resistor. Well, initially this circuit looks pretty ugly. There's quite a bit of stuff in it, right? But if we look back at our strategies, there's some things we can do here to make our lives easier. First, notice these two resistors here. Vx's resistor and the 2 ohm resistor are in parallel. They both experience the same voltage drop. So one thing you could do immediately is you could combine the parallel resistors. So that would be Vx's resistor, assuming you know the value, and the 2 ohm resistor. Let's continue with our strategies. So we already have a picture, and let's assume that we have our equation sheet in front of us. We've simplified our resistors, so let's check for anything special. Well, if we look at this circuit, notice that if we combine our 2 resistors together, we could indeed end up with a supermesh. So there is a supermesh due to the 3 amp current source. Before we jump in and start solving that supermesh, let's check the rest of our strategies. So we see the supermesh, so that gives us a hint we could do Kirchhoff's voltage law. But real quick, let's count those nodes and meshes. And if we count the nodes and meshes, you'd see in this case, it would actually be considerably easier to do node analysis for this question. So while you could certainly use that supermesh and try to solve for Vx using the supermesh, an easier approach might actually be to just use node analysis. Because looking at this whole circuit, we could actually write just a single node equation for Vx. So if we were to do a supermesh, we would need multiple equations because there's more than one mesh. So keep that in mind. In this case, the best approach, or at least one of the easiest approaches to find Vx, would actually be to use node analysis in this particular question. And again, definitely keep practicing questions like this, as you will find as you have practiced more and more questions, being able to recognize these different tools will become easier and easier. Lastly, notice you could have also checked the sources, and some of these resistors could have also been source transformable. For example, we could have done a source transformation on the 3 amp current source and the parallel resistor. So source transformation could have potentially worked there. But given that we're trying to solve for Vx, once again, node analysis would likely be the most convenient approach. Definitely keep these tools in mind. So before we move on, I'd also like to point out a few common errors that I see that are very important to watch out for when you're simplifying your circuits. First thing to note, remember you can walk along a circuit to determine whether things are in series or in parallel. For example, if I were to walk from point A to point B on this bridge circuit, notice I have two paths that experience the same voltage drop. So I can determine that my 2 kilo ohm and 4 kilo ohm resistors must experience the same voltage drop. There's two possible paths. And then similarly, when I'm kind of halfway through my circuit and I want to keep walking, notice once again, I can choose either the 8 kilo ohm or 6 kilo ohm path. Both of those paths would have the same voltage drop between the middle of my bridge circuit and point B. So notice how by analyzing this sort of diamond-shaped circuit, I can determine that this circuit is actually two sets of parallel resistors. And that makes this circuit quite a bit easier to solve. So definitely remember that components in series will experience identical current, and there is only one possible path for that current between the series components. Remember, components in parallel must experience the same voltage drop, and there are multiple simultaneous paths that current can take. Another thing to be very careful of is this second point. This is an extremely common mistake. Just because resistors appear parallel does not guarantee they are truly in parallel with each other. So, for example, if we look at this 6 ohm and 3 ohm resistor, they appear parallel to each other because they're both oriented vertically. The 6 ohm and 3 ohm resistor, they experience different voltage drops. Notice if I were to go from point VA to point VB, the 6 ohm resistor has a voltage drop of VA minus VB. If I go across, notice in order to get that same voltage drop VA minus VB, I would have to walk through both the 6 volt source and the 3 ohm resistor. So the 6 ohm resistor and 3 ohm resistor are not in parallel with each other. So be careful when applying those strategies to simplify. You want to make sure that you correctly recognize that circuit elements are in series or in parallel, because if you misinterpret that, that could cause you to make significant errors in the question. All right, so with those strategies in mind, let's go ahead and briefly review from our previous video, and then we will move on to Thevenin's theorem. So last time we covered source transformation and superposition. You'll recall that source transformation allows us to replace a voltage source and series resistor with an equivalent current source and parallel resistor. And notice this transformation can go in both directions. So we could also replace a parallel current source and parallel resistor with a series voltage source and series resistor. However, make sure you remember to use these relations to ensure that you replace with an equivalent source. Next, we have superposition. Superposition tells us that the response of a linear circuit to several inputs together, that response is equal to the sum of the responses with each input working separately. So here when we say inputs, that means independent sources. And you saw, as we had explained in our previous video, if we have a circuit that contains a current source and a voltage source, we can actually split that circuit into the sum, where we have a current source only, voltage replaced with a short, and voltage source only, current replaced with an open. We can determine the voltage that we care about with each source considered separately, then sum these two voltages to determine the desired voltage with both sources acting together. And as we learned, as long as our circuits have linear behavior, then both of these tools can be used. Let's go ahead and do one more review question before moving on. So here we are asked to use a source transformation to determine the values for the voltage source's voltage and our series resistor's resistance. So just to remind everyone, make sure you keep these equations handy. These are our source transformation equations. In this question, let's look at what we know. We know that we have a parallel current source with current IP is 2 amps. We also have a parallel resistor with 8 ohms resistance. We want to find our voltage Vs, and we know that would be given by Rp IP. And we also want to find Rs, which is equal in this case to Rp. So all we need to do is use those equations. We know Rp is 8 ohms, so we know that Rs must be 8 ohms as well. And finally, Vs equals Rp IP. So Vs, we can plug and chug. We have our Rp value, which is 8 ohms. We have our current, which is 2 amps. 8 ohms times 2 amps. That will give us our Vs is 16 volts. One more thing to watch out for is remember that we need to maintain the relative polarity of our voltage and current source. So notice the current source's arrow and the plus terminal of the voltage source need to stay pointing in the same direction. If not, you would need to multiply by -1 in order to reverse the direction of your polarity. All right, so once again, source transformation is pretty straightforward, but keep those equations handy so that you don't accidentally get anybody mixed up. Let's go ahead and continue on with our new topics for today, which are Thevenin's theorem and Norton's theorem. Before we dive into these, let's first cover a few quick key terms. We're going to see over the course of this class that Thevenin and Norton's theorems often become important when we're talking about sources and loads. And so often we design and think of electrical systems as having these two main parts. The source is the thing that supplies power to our system. And the load is the thing receiving that power. The load is the thing connected to the source. As you see in this figure, our source could be like our power outlet, right? And then maybe we're plugging in our electric vehicle. So examples of sources basically anything that provides power into our circuit. So that could be an amplifier, generator, power supply, voltage or current source. And then loads could be just about anything. It could be your cell phone, your laptop, loudspeaker, electric motor, antenna, many possible loads that we could have. And very often the load will be varied while the rest of the system stays fixed. For example, with a power outlet. Hopefully the power outlets remain standard throughout wherever you live, but depending on what you're trying to do, you might plug in your cell phone, your computer, you might plug in a kitchen appliance. So the load of your circuit may vary while the source stays fixed. And the reason we mention source and load here is because when we start talking more about Thevenin and Norton and equivalent circuits, sources and loads commonly come up when we work with equivalent circuits. Let's talk a little bit more about why we as engineers might care about these circuits. Why do we care about sources and loads and these equivalent circuits? Well, suppose that you are an engineer working in industry and your team wants to design a cell phone. The truth is, you're not going to be able to sit down and finish that design in one day. You can't just have everyone sit in a room and bam, the design appears. It would be nice if it was that simple, but most of the time, you're going to need to divide and conquer. And each member of your team may need to design a different piece of the overall circuit and the overall device. This figure shows a very rough schematic or block diagram of the things that would need in a cell phone. So you can see, for example, we have an antenna that is transmitting and receiving signals. And we also have input and output for voice and video. There's an external interface like buttons and memory. We have microprocessor. And notice there's all this stuff inside the phone to process the signals and convert them from some frequency that the antenna uses back into actual visual pictures and hearable audio. So there's a lot of conversion and filters and modulation that must be done in order to process the data that your phone sends and receives. So equivalent circuits can be extremely powerful when you need to design something big. Because what you can do is you can divide up your bigger circuit and temporarily replace chunks of your circuit with equivalent circuits. So you could tell somebody, okay, for your amplifier, you get up to 12 volts and you get some resistance, and we temporarily put this equivalent circuit here, and then we fill in with the actual details once we know what the amplifier looks like. So this is one way that we can use equivalent circuits to help us design a bigger, more complex circuit. Here's another area where equivalent circuits are incredibly useful. Suppose we have one large circuit and part of our circuit is really ugly. Right? Like suppose you have a really ugly portion of your circuit connected to some other part of your circuit which is not ugly. So, wouldn't it be nice if instead of having to study and look at this ugly circuit, we could instead replace that ugly part with something nice? So, it'd be really nice if we could do that, right? take something nasty and replace it with something simple that is electrically equivalent. So here's some good news. The good news is that it is always possible to view even a very complicated circuit in terms of much simpler equivalent source and load circuits. So what we're saying is that it's actually possible to do this. We can take an ugly circuit and replace it with a simpler equivalent circuit. And one way that we do this is by applying Thevenin's theorem and Norton's theorem. We make what's called the Thevenin equivalent circuit or the Norton equivalent circuit, and we can use that to simplify our circuits. So that brings us to today's class. So remember, last time we covered source transformation, superposition. So today we'll go ahead and look at Norton's and Thevenin's theorems. Here's a high-level definition, and we'll dive into the details in just a moment. We will see that Thevenin's theorem allows us to replace part of a circuit with a voltage source and series resistor. Notice we're just replacing a piece of our circuit. So the rest of the circuit is unchanged. Similarly, Norton's theorem allows us to replace part of a circuit with a current source and a parallel resistor. Once again, we are just replacing a part of the circuit that we don't like. So the rest of the circuit that we don't replace remains unchanged. And next time, we will look at maximum power transfer. And we will see actually that Thevenin's theorem is extremely useful when we apply maximum power transfer. So why do we bother with Thevenin's and Norton's theorems? Why are they so great? So once again, one of the big advantages of Thevenin's theorem and Norton's theorem is that we can replace everything we don't like. Basically, we can just partition off the stuff we don't like in our circuit, and we can replace everything on one side of a pair of terminals by an equivalent circuit. So notice the stuff we don't like that's attached to this circuit on the right. We can take this ugly stuff, and by Thevenin's theorem, we can replace the ugly stuff with a voltage source and series resistor. Or maybe we want a current source instead, then we apply Norton's theorem, and we replace that ugly portion of our circuit with a current source and a parallel resistor. And we will see both during this video and in future videos throughout the class, we're actually going to use this quite a bit. And we'll see that Thevenin's and Norton's theorems are really useful for simplifying uglier circuits. We can use it for maximum power transfer, and we can determine the effects of different loads in our system. So let's take a closer look at Thevenin's and Norton's theorems, and we'll also review procedure on how to determine these equivalent circuits. So here's an official definition of Thevenin's theorem. Thevenin's theorem says that any linear circuit can be replaced by an equivalent circuit containing a single voltage source and a single resistor. And the voltage of that equivalent voltage source, that is called our Thevenin voltage. And then the resistance of that single series resistor, that is called our Thevenin resistance. And you'll see some textbooks will abbreviate Thevenin voltage VT or VTH. Thevenin resistance is often shown as RT or RTH. And then the entire circuit that results, basically this voltage source and series resistor, that is also referred to as the Thevenin equivalent circuit. So if a homework problem asks you to find the Thevenin equivalent circuit, what they're asking you to find is the Thevenin voltage and the Thevenin resistance, and then to draw the two together. Norton's theorem is very similar to Thevenin's theorem. So Norton's theorem tells us that any linear two-terminal circuit can be replaced by an equivalent circuit consisting of an independent current source, which is in parallel with a resistor. And notice the naming again. The current source will have a current value called IN. That is our Norton current. So the current value of that equivalent current source is called the Norton current. And similarly, the resistance value of the equivalent resistor is called the Norton resistance. So once again, the equivalent circuit that results from Norton's theorem is called the Norton equivalent, where the current is given by the Norton current IN. Norton resistance is the resistance of that circuit. So you might have noticed we just talked about source transformation in our previous video. And hey, would you look at that? Norton and Thevenin are both related by a source transformation. Remember, if we have a voltage source with a series resistor, we can apply a source transformation to determine an equivalent parallel current source and parallel resistor. So what that means is that if we know our Thevenin equivalent, or if we know the Norton equivalent, we can easily do a source transformation to find the other one. So as shown here, we know that the Norton resistance and Thevenin resistance are actually equal by source transformation. And similarly, we know that the Norton current is equal to our Thevenin voltage divided by our Thevenin resistance. It's actually some very good news, because it turns out when we're learning our Thevenin equivalent and Norton equivalent circuits, we don't have to learn two separate procedures. So what I recommend you do is that instead of trying to memorize how to find Thevenin and how to find Norton, instead focus on learning how to find the Thevenin equivalent. Because once you find the Thevenin equivalent, all you need to do is use a source transformation to determine the Norton equivalent circuit. And often we find that it's a little bit more straightforward to determine the Thevenin equivalent for the types of problems we encounter. So let's go ahead and now discuss how would we determine our Thevenin and Norton equivalents. What do we actually need to do? So it turns out there's two cases for Thevenin's and Norton's theorem. If our circuit contains no dependent sources, then we follow the procedure shown here. If our circuit does contain dependent sources, there is a slightly different approach we must follow. So again, be careful to check for dependent sources. Remember, this approach is for circuits which do not have a dependent source. We'll cover what to do if we have a dependent source in just a moment. Okay, so here's how we find our Thevenin and Norton equivalent. First, if you need to, you want to determine what part of the circuit you want to find Thevenin of. And so if your circuit's already attached to a load, you might want to separate the source from the load. Keep in mind you want to keep the dependent source and any controlling part of that dependent source together. Next step, you want to find the Thevenin voltage. Turns out that our Thevenin voltage Vt is equal to VOC. Remember the open circuit voltage? Open circuit voltage is the voltage across the two open terminals. So if we were in the lab, we could just put a multimeter. Just measure this with a multimeter. Right? Like we could actually put the red probe of the multimeter on the positive end and the black probe on the negative end. And we could actually measure what that open circuit voltage is. But of course, if we're solving the circuit on paper, then we need to actually mathematically solve for that open circuit voltage, which is the voltage across the two open terminals. Once we find the Thevenin voltage, we next need to find Thevenin resistance. So once again, if we were in the lab, how we would do this is in lab, we would turn off the independent sources and then use an ohm meter, or just use a multimeter to measure resistance across the terminals. Right, because we could just take our multimeter and then change it to measure resistance, turn off our voltage source, and we would determine what our Thevenin resistance is. But of course, on paper, we have to instead do the same thing, but using our circuit on paper. So to find Thevenin resistance with our hand calculation, we have to replace our independent voltage sources with shorts or a plain wire. And we replace our current sources with open circuits or broken wires. That essentially turns off those independent sources. And once we've turned off those sources, we calculate our resistance when we go from one terminal to the other. So in this case, I would go from this terminal A to terminal B. I would walk along those terminals and calculate how much resistance do I see when I pass from the first open terminal to the other one. Notice once I have found my Thevenin voltage and Thevenin resistance, then I am finished, and I simply replace the circuit that I had with the Thevenin equivalent, where my voltage is Vt and my resistance is Rt. And remember, if I wanted to find the Norton equivalent, then I just do a source transformation. So I could determine that my Norton current is just Thevenin voltage divided by Thevenin resistance, and use the Thevenin resistance as my Norton resistance. All right, so the best way to get comfortable with this procedure is to do as many examples as you can until the procedure makes sense. So let's do some examples now. Let's start with a fairly simple one. Suppose we want to find the Thevenin and Norton equivalents for the circuit shown here. So in this case, let's think about how we would approach this question. Remember, our first step is to find VOC, our open circuit voltage. Then we turn off independent sources. Remember, voltage gets a short, current sources get an open. Then we find our Thevenin resistance by calculating the resistance when walking from one open terminal to the other. So in this case, if I have terminal A and terminal B, notice I would turn off my voltage source and I would need to walk from A to B through those resistors. So let's go ahead and first begin with finding our open circuit voltage. Well, let's take a look and see what is our open circuit voltage in this case. So here you want to notice, and for this circuit, VOC is the voltage across our 4 ohm resistor, or voltage across 2 ohm resistor and 8-volt source combined. So big caution here. This is a very common mistake for beginning students. Caution. Our VOC value is not equal to 8 volts because my VOC is my voltage from one open terminal to the other. Notice in order to experience my voltage drop from A to B, I have to go through either the voltage drop across my 4 ohm resistor to go from voltage at A to voltage at B, or the voltage across my 2 ohm resistor plus the voltage across my 8-volt source. So be very careful there. Make sure you calculate your open circuit voltage correctly. So in this case, let's determine VOC across the 4 ohm resistor. How would we approach that? If you're not sure, remember those rules we covered. And based on those rules, you could consider counting the number of nodes and meshes in your circuit. And if you do that, you could see, in this case, there's a few different approaches. You could do a node analysis using the node right at point A. You could also apply Kirchhoff's voltage law and recognize that the 2 ohm and 4 ohm resistors are in series with that 8-volt source. In this case, I'm going to go ahead and use that series relationship. I'm going to notice that the 2 ohm and 4 ohm resistors are in series with my 8-volt source. That means we can use voltage division. And in this case, we can determine that the voltage across our 4 ohm resistor must be equal to VOC. And again, that's just 4 ohms divided by 4 ohms plus 2 ohms times our source, which is 8 volts. So VOC is going to be 4 over 6 times 8. So we determine VOC is equal to 32/6 thirds times 8, 20/16. It's about 5.33 volts. That means our Thevenin voltage is 5.33 volts. That wasn't so bad. Notice you do need to be able to recognize what tool in your toolbox will help you most conveniently find VOC. So our second step is to turn off independent sources and find our Thevenin resistance. So let's do that next. So remember, we first have to turn off independent sources. So that means our voltage source becomes a short. Everything else remains the same. So we still have a 2 ohm resistor up top and a 4 ohm resistor down below. Then we need to find the resistance when walking from A to B. So here's another area where you need to be careful. Pay attention to whether the resistors are in series or parallel. Remember, you are walking through the circuit. From one open terminal to the other. So notice here, if I'm walking from A to B, I have two possible paths. And so I need to notice, in this case, the 2 ohm and 4 ohm resistor are in parallel. Be careful. They might have been in series with the voltage source, but relative to terminals A and B, Relative to terminals A and B, those resistors are in parallel. That means that the resistance from A to B is equal to our Thevenin resistance, which is equal to 2 ohms in parallel to 4 ohms. So in this case, if we go ahead and solve, we determine our Thevenin resistance is just 2 times 4, 2 plus 4, which is 8 over 6, or 4/3 ohms. Remember, our goal was to find both Thevenin and Norton equivalents. So we know that our Thevenin that's just going to have our Thevenin voltage of 5.33 volts and our Thevenin resistance of 4/3 ohms. And then remember our Norton, we know our Norton current is simply equal to our Thevenin voltage over Thevenin resistance. So our Norton current is basically 16/3 divided by 4/3 equal to 4 amps. So our Norton equivalent will be a 4 amp current source with a 4/3 ohm resistor in parallel. So there you have it. We have successfully determined our Thevenin and Norton equivalents for this circuit. So let's go ahead and try another example. And again, this process might seem unusual at first, but please keep doing examples until you get comfortable with these procedures. You'll see that being able to easily find Thevenin and Norton will make your life so much easier. Let's try this next example. Now we want to find Thevenin and Norton for this circuit with resistors and a current source. And we can use the same procedure as we just learned. Let's first start with a question. Does any current flow through our 3 ohm resistor? Take a moment and think about it. Does any current flow through that resistor? The answer is no, right? Because a 3 ohm resistor is connected to an open. So, for the purposes of our Thevenin voltage calculation, we can assume, in this case, that this whole top part of the resistor, this whole top part of the circuit, relative to the ground, we can assume that our Thevenin voltage is the voltage difference between our top node and the ground. So we can assign a ground on the bottom end of that circuit. This can be a very helpful strategy. So if you see resistors for the purpose of Thevenin voltage, remember no current flows through that 3 ohm resistor, so its impact on the circuit can be essentially ignored, at least for the Thevenin voltage. We do need to consider that 3 ohm resistor later when we calculate the Thevenin resistance. So let's go ahead and determine our Thevenin voltage. And as we mentioned, in this case, we notice that basically this whole area we can treat as our Thevenin voltage relative to the ground. So how could we find our Thevenin voltage for this circuit? Given the strategies that we covered at the beginning of the video, what approach might work best? Take a moment and think about it. Here's what I recommend. First, combine the 4 ohm resistors, and then we can do node analysis. Notice that there's basically just one node in this circuit. And so node analysis would be a really convenient way to directly solve for VT. So if I have two 4 ohm resistors in parallel to each other, that's just 4 times 4 over 4 plus 4, which is 16 over 8, or 2 ohms. So if we replace those two parallel 4 ohm resistors with an equivalent resistor, we get a 2 ohm resistor at 3 ohms on the top right, and then we have 1 ohm on the top left, and 3 amp current source. Now our goal is to find VT. So I'm going to go ahead and do node analysis just at these two nodes, and I can determine that I have plus 3 amps coming in minus VT divided by 2 ohms equals 0. So I can go ahead, solve for VT. Remember, there is no current going through this 3 ohm resistor because it's open. So if I solve for VT, I determine that in this case, VT over 2 is equal to 3 amps. Thevenin voltage VT, that's just going to be 6 volts. Well, that's not so bad. Next, we can find our Thevenin resistance. So remember, we need to turn off the independent sources. So our current source becomes an open. So be careful there. Remember, current sources become opens, not shorts. So a common mistake is to accidentally replace a current source with a short, which is incorrect. Remember, current sources become opens. So we're left with something like this. And I'm going to go ahead and leave my 2 ohm equivalent resistor in there. And remember, now I need to find my resistance when walking from terminal A to the other open terminal, terminal B. So notice the only path I can take is through the 3 ohm and 2 ohm resistors. Notice the 1 ohm is connected to an open, so I can't pass through. Therefore, my equivalent resistance is just a 3 ohm plus 2 ohm resistor in series. It means my Thevenin resistance is 5 ohms. Not so bad, right? Just remember to follow the procedure carefully. So last step, we need to find both the Thevenin and Norton equivalents. So remember, the Thevenin equivalent, that's just going to be our Thevenin voltage, which we determined was 6 volts. And we have that 5 ohm resistor in series. And for Norton, we know that Norton current is Thevenin voltage divided by Thevenin resistance for 6 volts over 5 ohms, which is 1.2 amps. So Norton will be 1.2 amps with a 5 ohm resistor. So there you have it. Let's try one more, slightly more complex example before we look at dependent sources. So here we want to find Thevenin equivalent, and now we have both an independent voltage source and an independent current source in this circuit. And notice we're trying to find the Thevenin equivalent of the circuit connected to R. So basically, we're looking at the portion, the circuit connected to the load R. So let's follow the same procedure. First, we need to find VOC, which is our open circuit voltage. So notice that in this case, we can basically ignore the load resistor. Basically, we just unplug it from our circuit. So I'll just go ahead and white it out because for us, we only need to consider the circuit connected to that resistor. And so here we want to find the OC. Does any current flow through that 2 ohm resistor? No, remember this is connected to an open, so no current flows due to the open. So it turns out, once again, if we let a ground be down here, we can recognize that in this case, VOC is the node voltage of the top node relative to the ground. So here I'm assigning my bottom node to be ground so that I can determine that VOC. How can we find VOC? Well, there's a couple ways we could do this. We have a shared current source, so we might be thinking super mesh. But notice in this example that once again, that node VOC is awfully convenient. And so for this particular example, I would actually recommend doing node analysis once again. So if you have a circuit like this, Notice node analysis would be a convenient approach because you can write just one equation for VOC. So in this case, I'll go ahead and label some currents. So I will say by Kirchhoff's current law, plus I1 minus I2 minus I3 equals 0. Remember, no current flows through the 2 ohm resistor, so don't need to worry about that. So if we substitute our currents, notice we have that I1 is equal to 24 volts minus VOC divided by 6. Then we have minus 7 amps exiting, minus VOC divided by 12 ohms exiting. All that must equal 0. If we multiply both sides by 12, we end up getting 2 times 24 minus VOC. Then we have the minus 7 amps, that becomes minus 84, minus VOC equals 0. And notice here we can simplify further, so we have 48 minus 2 VOC minus 84 minus VOC equals 0. So we have 48 minus 84. So if we combine those two terms, we will determine that we have 36 there, right? Negative 36 minus 3 VOC equals 0. So 3 VOC is negative 36. We determine our VOC is negative 12 volts. All right, so there's our VOC. Next, it's time to find our Thevenin resistance. So remember, first we have to turn off the independent sources. And then we need to find resistance when walking through the circuit from one open terminal to the other. So in this case, if we go ahead, give that a try, remember once again, we still have our load resistance disconnected because we're only interested in the part of the circuit connected to that resistor. So 7 amp source becomes an open, 24 volt source becomes a short. Let's draw what we get. So one common mistake here, we do need to consider the 2 ohm resistor remember to consider the 2 ohm resistor when finding resistance. So remember, we were able to ignore that 2 ohm resistor during our Thevenin voltage calculations, but here, if I am walking from my terminal A to terminal B, notice that I have to pass through that 2 ohm resistor. So we see we have a 2 ohm resistor in series with a 6 ohm and 12 ohm in parallel. So that means our Thevenin resistance is just going to be 2 ohms plus 6 times 12 over 6 plus 12. That gives us 2 ohms plus 72 over 18, which is 2 ohms plus 4 ohms. We determine our Thevenin resistance is 6 ohms. So notice it's just a coincidence in this case that our Thevenin resistance happened to be the same as a 6 ohm resistor up top. Notice that in order to find Thevenin resistance, we had to consider all of the resistors in our circuit. So finally, that leaves us with our Thevenin equivalent. In this case, we determined our Thevenin voltage and resistance. So the Thevenin equivalent of the circuit connected to R is just going to be our 6 ohm Thevenin resistance. And remember, our voltage source we determined was minus 12 volts. So there you have it. All right, so let's go ahead now and look at the one other case for Thevenin and Norton when we do have dependent sources. So remember, the procedure we covered up to this point was for Thevenin and Norton without dependent sources, but if we do have dependent sources, the procedure is different. So make sure that you follow the correct procedure. If you have a circuit with a dependent source, you need to make sure you follow the slightly different procedure for finding Thevenin resistance. So again, be careful. Slightly different procedure for Thevenin resistance with the dependent source. So you'll see we follow the same exact approach as we did before for Thevenin voltage. So Thevenin voltage procedure is the same. For Thevenin resistance, the first two steps are the same. You would find that you need to turn off your voltage and current independent sources. But when you have a dependent source, you can't easily turn off the dependent source. So what we do instead is we connect an imaginary external source, I call it VEX, and we use the fact that Thevenin resistance is given by voltage divided by current, so we can basically find an expression for VEX in terms of the source's current IEX. And then we use that to find our Thevenin resistance. Then, like before, we determine our Thevenin equivalent, and we can use a source transformation if we want to find Norton equivalent. Let's go ahead and give this a try. So here we have a Thevenin equivalent that we want to find, and in this case, we want to find Thevenin equivalent of a circuit with a dependent source. Let's go ahead and see how we would do this. So remember, we can follow the same procedure as before for Thevenin voltage. So here we want to find our open circuit voltage. And notice in this case, no current will go through the 3 ohm resistor. At least not yet, right? So we can go ahead and apply our usual techniques to determine VOC. And so in this case, if we want to find VOC, node analysis would be convenient once again, because we have a very convenient node up here for VOC. No current flows through there, so VOC would just be the difference between our top node and the bottom portion of our circuit. So let's go ahead and apply node analysis. So if we apply node analysis here, notice we do have that IA that our dependent source depends on. And since this circuit is a closed loop, we can determine that IA must be traveling around my circuit counterclockwise. So notice what happens if I want to apply node analysis at that top node. Let's go ahead and draw in some currents. So in this case, let's say I have I1 exiting my node. Maybe I have I2 entering. So I could say plus I2 minus I1 equals 0. Or I can say, in this case, I can say I have VOC minus 12 volts divided by 6 amps, or divided by 6 ohms. That's my I1 that's leaving. So again, VOC minus 12 volts divided by 6 ohms. And my current I2, notice that is going to be given by my IA value. So I can write, in this case, that IA minus VOC minus 12 over 6 equals 0. Well, I need another equation relating IA and VOC. Notice the dependent source. Notice that my VOC is actually equal to 2IA because the voltage difference between my ground and point VOC is given by that dependent source. So this is the second equation that I need. I can take this equation and substitute it back in. And in this case, I'll go ahead and solve for IA. And I can determine IA minus, substitute for VOC, I will say minus 2IA minus 12 over 6 equals 0. Multiply both sides by 6. 6IA minus 2IA minus 12 equals 0. So I determine that for IA, oops, and be careful there. Just noticed I made a small mistake. Notice the minus sign has to be carried through. So this is actually plus 12. Be careful of sign errors. So now we go ahead and solve for IA. So we determine for IA is equal to negative 12. So IA must be negative 3 amps. Since VOC is 2IA, we can determine that VOC must be our Thevenin voltage, Thevenin voltage must be equal to negative 6 volts. So don't worry too much if you see negative numbers for these Thevenin voltages, because remember, at the end of the day, we're trying to find an equivalent circuit. So depending on the dependent sources and other things in your circuit, it is actually possible for both Thevenin voltage and Thevenin resistance to be negative. Okay, so we found our Thevenin voltage. It's time to use our slightly different procedure to determine our Thevenin resistance. So remember, because we have a dependent source, we need to follow the correct procedure. So we need to follow the procedure for the Thevenin resistance with dependent sources. So we still turn off our independent sources, but then we need to connect the external source, VEX, with current, IEX. Then we need to solve for VEX divided by IEX. So if we do that, notice a 12-volt source, that's going to become an open, or this will become a short. And so we're left with something like this. So here I'm going to rewrite my IA as IA prime. And that is because we took away this voltage source, so IA is no longer going to be the same IA as before. So remember, the current will be different with the 12-volt source turned off. So I put the prime there mainly to avoid confusing myself. Even though we had determined IA in the previous part of the question, it's not going to be the same as this IA. It's still our dependent source. It will still depend on IA prime. And of course, we have a 3 ohm, 6 ohm resistor. And now we connect that external source. Our task here is to find expressions for Vx over IEx. And we know RT is Vx over IEx. So how do we do that? Well, a good place to start would be node analysis, because we have a really convenient node right here, right? Let's go ahead and start with some node analysis. There's one other thing we can do to make our lives a little easier. Notice the 3 ohm resistor is in series with VEX. So I can actually move my 3 ohm resistor to the top part of this circuit because VEX and 3 ohm, they're in series with each other. The current has to pass through both of them. So it is legal. I can reverse the order and have no effect on my circuit. So because VEX and 3 ohm resistor in series with each other, I can move the 3 ohm resistor to the top. Because as long as it stays in series, that's legal. I'm going to do that because that helps me with node analysis, and then I can let my ground node be at the bottom of VEX. So let's go ahead and do our node analysis. And if we do that, we can determine, in this case, let's do a node analysis to find our node here. And so what we can determine is we can determine that voltage. So here I know that I have 2IA prime volts at that node, right? Because of the dependent source. So I can write that IEX must equal VEX minus 2IA prime divided by 3 ohms. Right? That's the node equation through the 3 ohm resistor. Ohm's law on the 3 ohm resistor. So that's a step in the right direction, but notice I need to find that expression for VEX over IEX. I need to get rid of IA prime by finding a second equation. I need to find another equation for VEX, IEX, and IA prime. So it might be a little tricky at this point to figure out where else can I get another equation. Notice that the left-hand loop we have not yet considered. So let's try applying Kirchhoff's voltage law to our left loop. And if we do that, notice what we get. We can determine, if I just walk in the counterclockwise direction, I determine that plus 2IA prime minus the voltage drop across that 6 ohm resistor, that must equal 0. And wait a minute, well, we know that current IA prime must be flowing through the left loop, right? Because we're told IA prime is flowing throughout that left-hand loop. So that means 2IA prime minus V6 ohms, that's minus 6 IA prime equals 0. This must be true by Kirchhoff's voltage law. Well, wait a minute. The only way for negative 4 IA prime to equal 0 is if IA prime equals 0. Well, there's our other equation. So we can plug in 0 for IA prime, and we can determine IEX equals VEX over 3, or VEX divided by IEX is going to equal 3, so our Thevenin resistance is 3 ohms. And there you have it. So as you can see, these dependent source questions can be a little more tricky. So it's very important that you draw pictures, practice this procedure, and make sure you get comfortable finding equations for these unknowns. Let's go ahead and try one last example before we end for today. This was actually a past exam question that I gave, and here we're asked to find the Thevenin equivalent for this circuit connected to the load. Take a moment, and I'd encourage you, try attempting this one on your own, and then watch the recording to see if you got the answer correct. Let's go ahead and talk through how we would approach this. And my first recommendation here would be to just follow our procedure step by step. Remember, our first step is to find the OC. Once again, we can neglect the load portion of the circuit because we don't care about that. And remember, we can recognize that no current flows through the 10 ohm resistor. So for the purpose of Thevenin voltage, we know that we have a very nice node right up here. So the key to this question was first recognize that the top node voltage is VOC. And then we can treat the bottom as our ground. There's several ways we could approach this question. Notice we could combine the 2 ohm and 1 ohm resistors. So we can go ahead and do that. So in this case, notice a 2 ohm and 1 ohm, they are in parallel with each other. And so it's again 2 ohm parallel to 1 ohm. That's just 2 times 1 over 2 plus 1, or 2/3 ohms. So we replace 2 ohm and 1 ohm resistor with a single 2/3 ohm resistor. And notice we do have a dependent current source dependent on 2Vx. And for now, we ignore that 10 ohm resistor. Also notice that Vx is also equal to our Thevenin voltage for this particular question. Let's go ahead and try node analysis here. So in this case, I'm just going to go ahead and label some currents. So I'm going to say minus I1 minus I2 plus I3 equals 0. So I determine I have minus 30 amps. 30 amps is leaving. I have I2, that is just minus VT over 2/3. And then I also have 2Vx coming in. So remember, Vx is equal to Vt, so I'm just going to go ahead and call that plus 2Vt equals 0. So if I rearrange, I determine that I get minus 3/2 Vt plus 2Vt equals 30. Solving for Vt, I determine 0.5 Vt is equal to 30. That means Vt is going to be 60 volts. All right. Next, we need to find our Thevenin resistance. And notice in this case, we do need to include the dependent source. So we got to be careful there. But actually, this question is otherwise fairly straightforward. So we already combined the two resistors in our previous part, so I'm going to keep that combined 2/3 ohm resistor. And remember, I do need to turn off the independent sources. That means my current source should be replaced with an open. And then I also need to connect the external source, VEX, find VX over IEX. So let's draw what we get. Remember the 30 amp source, that becomes an open, so we basically ignore that. We get our 2/3 ohm resistor. And here I'm going to call my voltage Vx prime, because since we turned off our current source, that Vx value will likely be different. We can't assume it's the same as what we had before. Similarly, our dependent current source becomes 2Vx prime, and we do have that 10 ohm resistor in there. And we do connect our external source VEX that supplies current IEX. Once again, we now need to find expressions to determine VEX over IEX equals RT. So a good strategy here is to use node analysis again. We can easily find IEX through that 10 ohm resistor. Over here, we're sitting at Vx prime volts. So we can say that VEX minus Vx prime over 10 ohms equals IEX. Once again, we need a second equation to relate VEX, IEX, and Vx prime. So in this case, let's go ahead and do node analysis, because that would be an easy way to get an equation for Vx prime in terms of the other values. So if I just do a node equation, notice I can just draw in some currents. I can say minus I1 plus I2 plus IEX equals 0. And in this case, my current I1, that is just going to be Vx prime divided by 2/3 ohms. So that's minus Vx prime over 2/3 plus I2, that is plus 2Vx prime plus IEX equals 0. That gives us minus 3/2 Vx prime plus 2Vx prime plus IEX equals 0. We determine, in this case, 0.5 Vx prime equals negative IEX. Or we can say, in other words, that IEX is equal to negative. So I can say Vx prime is equal to negative 2 IEX. Notice now that I have that, I can plug it back in to my other equation. And I can determine VEX minus negative 2 IEX. So again, watch the negative signs. VEX minus negative 2 IEX over 10 equals IEX. So I can write that VEX plus 2 IEX equals 10 IEX. VEX equals 8 IEX. So VEX over IEX is equal to 8. And then that means our Thevenin resistance is 8 ohms. Thevenin equivalent, therefore, becomes 8 ohm resistor with our 60 volt source. So this was definitely a more tricky question, but if you are comfortable with our procedures and follow the steps carefully, you should be able to come up with this result. So this concludes our video for today. So hopefully now these strategies to determine which approach to use are starting to become a little more clear. So I highly recommend, as you approach the Thevenin and Norton problems and other circuit problems in the coming lectures, keep those strategies we covered in mind. With Norton and Thevenin and the more complex circuits, sometimes it's a little tricky to recognize which strategy to use, but by practicing more and more questions, you'll build that intuition and things will get easier. Also, keep practicing Thevenin's and Norton's theorems. These are really powerful tools that we will use throughout the course. And please do take some time to go back through these examples on your own to gain extra practice. You'll find once you get the hang of Thevenin and Norton, the procedures are actually pretty straightforward. So thanks everyone for watching our video and joining the fun. Next time we will cover maximum power transfer theorem, which directly uses the Thevenin theorem that we covered today. We'll see you all in the next video. Thanks everyone.